Just wanted to go through some Snell's law examples with you. We defined Snell's law earlier, and the equation is right up here. You've got it also on your equation sheet. So just wanted to remind you of that. And we're going to go through those three problems that you have in front of you on that little half sheet of paper, and I've got them right here as well. So the first one says a ray of light in air is approaching a boundary with water at an angle of 52 degrees. It says determine the angle of refraction of the light ray. So not having done a problem like this before, I'm going to start out just kind of by drawing the picture to get a conceptual idea of what's going on. So there's my boundary. I'm going to do air up here and water down here. We can imagine kind of like we did with our marching, what's going to happen. So I'm going to draw my normal. Remember, normal just means perpendicular, nothing special about it besides that. We've got our light coming in at about 52 degrees. It hits the boundary. So here, this is my theta I, okay, of 52 degrees. We know that when it goes into the water, because the water is more optically dense, the water has a higher index of refraction, that it's going to go into the water here. It's going to bend toward the normal. And so that means that we know that our angle is going to be less than the 52 degrees that we had initially. It's always nice to be able to predict if it's going to be greater than or less than the original, just so that you know if you're doing it right as you're working through the problem. So not ever having done a problem like this before, we're trying to remember what to do. We're always going to go back to that guess method. So we're going to start with our givens. What do we know? So it looks like we know that we've got light going from air into water. And that's another thing that I often will do with these Snell's law problems is to write it out so that I don't forget. We're going from air to water. That means that I can write my indices of refraction. So Ni and Nr. There is a chart in your book that has the indices of refraction. I've also got them here on my notes. So we're going to go ahead and take a look. Air has an index of refraction of 1.0003. That's pretty darn close to 1. And for all of our purposes, we're just going to go ahead and call it 1. So that was the first one. The second one right here is water, which is 1.33. So I'm going to go ahead and write those down. So Ni is 1.00. We're going to call that pretty darn close to a vacuum. And then Nr is going to be 1.33. So that's the index of refraction of water. We know because the problem said that the initial angle, or the angle that it comes into the water at, is 52 degrees. So that's going to be my theta I. And the thing that I'm looking for, theta R, is the question mark. Okay, so that's the thing that we're going to try and solve for. We've got one equation that we know how to use for this stuff, so we're just going to go ahead and write it down. So that's Ni sine theta I equals Nr sine theta R. Okay, we are solving for this sine theta, or we're solving for the theta R. It's way over on that far side. So we just need to do some algebra to get our theta by itself. So right now we are multiplying by Nr, so we're going to divide by Nr on both sides. And then I've got Ni sine theta I over Nr is equal to sine theta R. So we're getting close. Remember, to undo multiplication, you divide. To undo the function of sine, you just do the inverse of sine. We've done this. It's been a while, though, and if you haven't done it in math lately, it may just not feel supernatural to you. So just a friendly reminder that that's what we're doing. So we're going to do the inverse sine. That's going to get rid of this sign here. And so then our expression for theta R is going to be equal to sine inverse of Ni sine theta I over Nr. At this point now, we just need to plug it into our calculator. So that might be a little bit intimidating to you. And if it is, I'm going to kind of talk you through it. I don't have my calculator here to show you what I'm typing in. So please talk to one of your classmates if you're confused about how to type things in. So inverse sine is the second sine button if you're using one of the TI-30 calculators that we have in the classroom. Okay, so you can do that and then put parentheses. Ni, we said, was 1. So I'm just going to do 1. And then I would type in times sine, in this case, it's 52. Okay, and I would do lots of parentheses here. Then you're going to do a divide by 1.33. So the biggest challenge with Snell's law is making sure to keep track of which ones are the I's and which ones are the R's, so that you get your indices of refraction correct, which one's on the top and bottom, and then also where everything else goes. So at this point, then you can just plug that into your calculator. Also, make sure that your calculator is in degrees. If you're doing radians and math now, make sure that you've got it set that way. I worked it out and got a value of 36.3 degrees. So hopefully you found that. Again, if not, talk to somebody around you and get some help. Okay, that number it does make sense to us because again, we're coming in at an angle of 52 degrees and we're going to come out at something smaller. 36 is definitely smaller than 52, so we're feeling good. All right, going to move on to number 2. So this one is similar, but it's a little bit more involved. So it says a ray of light in air is approaching a layer of crown glass at an angle of 42 degrees. It says determine the angle of refraction of the light ray upon entering the crown glass and also leaving the crown glass. So this one's just it's like a little bit of a sandwich question. So I'm going to go ahead and draw my boundary and I'm going to label things just to kind of keep track of what I'm doing. So I've got air, glass, whoops, my stylus is awesome. There we go. And then air again. So if we draw this light coming in, it says it's coming in at an angle of 42 degrees from the normal. Come on, there we go. All right, so we're going to go ahead and draw a normal. Draw this light coming in at 42 degrees, so something like that. And then, again, going from air to glass, it's going to slow down, which means it's going to bend toward the normal. So we're going to have an angle that comes in something like this. And then it's just going to keep going straight at that speed, so at that angle, all the way through the glass. We assume, I guess it doesn't really say, but we're going to assume that it's a parallel or flat piece of glass. If not, then it would certainly say that to us. So we're going to go ahead and assume that it's just like a window or something like that. Oops. And then it's going to bend when it gets to the air as well. So now we're going from a high index of refraction to a low index of refraction when we go from the glass into the air. So that means it's going to bend away from the normal. Whoa, that's supposed to be a straight line. Sorry, it's not very lovely. Okay, so I've got a theta here. I've got a theta here. We can prove that this theta, I'm going to call it theta 2, is going to be the same on both of these things. They're alternate interior angles, if you will. So hopefully that makes sense to you. Usually we use I and R for the incidence and refraction, but because we've got 2 sets, I don't want to get myself confused. I'm going to call this theta 1, the one inside the glass theta 2, and then I'm going to call this theta 3, just so that I can kind of keep track of what's going on. So let's go ahead and write down some givens so that we have a sense of what's going on. So again, we're going from air to glass and then back into air. So N1 is going to be air, so that's 1.00. N2 is crown glass. You're going to refer to your list. I'll go ahead and look over here. Crown glass has an index of refraction of 1.52. And then it's going to go back into air. So N3 is going to be the same as N1. It's going to be 1. Okay. We know that theta 1 is, it told us 42 degrees. And we're looking for both theta 2 and theta 3. So this is one of those sneaky problems where really we're just doing 2 problems in one. All we're going to do is focus first on this problem right here. That's all I care about, is just finding theta 2. And friends, this is exactly like the first problem we just did. Okay, so let's go ahead and work through that one, see how we do, and then we can jump into the next piece. So solving for theta 2. So N1 sine theta 1 equals N2 sine theta 2. Now the subscripts are different from the way I had it before. But again, I just don't want to use I and R because it's a little bit confusing since there are 2 sets of refraction. So what we're doing right now is we are solving for theta 2. We can do that, no problem. Same process that we did before. So we're going to do N1 sine theta 1 divided by N2. We're going to do the inverse sine, and that will give us theta 2. Hopefully that algebra made sense to you. If it didn't, go back and look at the process from problem 1 because it's the same process that we did before. So if I plug in some numbers here, that's going to be sine inverse of 1 times the sine of 42 divided by 1.52. So we expect when we find theta 2 that it's going to be something smaller than the 42 degrees because, again, we're bending toward the normal. And when we plug all of that in, we get, I believe, 26.1 degrees. Okay, so go ahead and work through that. Make sure that your answer matches mine. If you're not sure, it's better to advocate for yourself. Ask questions now because I promise you there will be a question like this on your quiz on Tuesday. Okay, so after we do that one, so that we found that first question, and then remember, this is just one of those sneaky things. I'm just going to give you 2 problems in one. So now we're going to focus on this bottom part. Okay, so now we're going to solve for theta 3. Same process. We've got n2 sine theta 2 equals n3 sine theta 3. So we're just looking at that second refraction. In this case now, we're looking for something that's going to be greater than the 26.1 because when it gets over into the glass, when it goes from the glass into the air, it's going to bend away from the normal. And so therefore, it's got to be a bigger value. Okay, same algebra that we've done before. You're going to get really used to this. And as long as you don't mess up your subscripts, this is really not a hard algebraic process. That's going to give you theta 3. So if we plug those values in, we're going to get sine inverse of, now n2, we have to make sure that we're plugging in the right values. n2 is 1.52 sine of 26.1. This is the value that we had right up here that we found in the first part, okay? Divided by 1.00. So it looks a little different than the ones we've seen before because now we're starting in glass and we're moving to air. So you have to make sure, again, that you're setting your N2 and N3 correctly so that you get the right result. If you look at this kind of from a mathematical perspective, having a higher index of refraction on the top is going to give you a higher angle, a bigger angle, because we're bending away from the normal. So when you plug that into your calculator, again, making sure you're in degrees, making sure that you're doing the inverse sine first and then the sine second, you will find, oh my goodness, that the angle is 42 degrees. Now, the lovely and interesting thing there is that it's 42 degrees when it's going in, and it's 42 degrees when it comes out. That means that the light that comes in and the light that comes out are parallel. This is a really nice thing. This is why you can see through a window without a lot of distortion, because all of the light is going to bend and slow down in the glass and then speed up right again when it leaves so that you see the same thing through the glass that you would see on the other side. So it's pretty cool. All right. Question 2, we're going to move on to number 3. Number 3 is kind of fun because it's got a piece of glass that is not flat. So in this case, we've got a ray of light approaching a triangular piece of crown glass. Hey, crown glass, we know that one. We've done that one already. This one, just making a note here, is, whoa, hello. I don't know what that was. That was like magic, but I don't even know what it was. That's crazy town. All right. The N of crown glass, let's look and see what it said before. Ta-da! Was 1.52. At an angle of 0 degrees. 0 degrees. That means that it's coming in straight head on, as shown in that picture. It says, perform the necessary calculations in order to trace the path of the light as it enters and exits the crown glass. Okay, so this one's going to take a little thinking, but you guys are good at thinking, so we got this. So you've got your light that's coming in. Here it comes. Let's see if I can highlight it. Are you going to let me or no? I think my stylus wants to go to bed. There we go. All right. Come on. There we go. So it's coming in here. This is like when we're marching with that medium change, and all that's going to happen is that our wavelength gets smaller, right? Or yeah, gets smaller because we're slowing down. Yep. So it's not going to bend. There's no bending that happens. So that means that the light just keeps on trucking. No refraction at that first boundary change because there's no reason for it to bend toward or away from the normal, right? It's already going in on the normal. Life is good. So now we've got this funny thing, because if this was a flat piece of glass, like in the last question, it would just keep going, no problem. But in this case, we've got this funny triangle, which means that we need to do some analysis and figure out what's going to happen here. So I'm going to draw a normal line. We're going to have to do a little bit of geometry thinking, and I know y'all love that, so let's just take a deep breath. We got this. So you've got this triangle down here. It's a 30, 60, 90 triangle. We know that because it's a right angle, and we know that that bottom angle is 30, so that means this one is 60. We know that the normal line has to be perpendicular to the side, which means that if that's 60, this one right here has to be 30, just like this one right down here. So that theta I in the glass is going to be 30 degrees. Ni is going to be, what was it, 1.52, I think? Let's find out. Where'd it go? There it is. Whoa, that's such a cute little measurement. So Ni is 1.52, theta I is 30 degrees, okay? Nr, we're going back into air. This is all air out here, so that's going to be 1.00, and we just need to find theta R. I think we can handle it. We've done it a bunch of times. Let's do it again. Here it comes. Oops, let me see if I can write it out correctly. Ni sine theta I equals Nr sine theta R. We've got this, no problem. So we're just solving for theta R. Hey, it's the same darn algebra that we've done a million times. So we're going to do Ni sine theta I over Nr, inverse sine, equals theta R. Let's plug in our numbers. So sine inverse of Ni, again, it's that bigger one, right? It's 1.52 times the sine of 30 degrees. Hey, and what do we think? Is it going to be bigger or smaller? Let's think about it. We're going from glass into air. That means that it's going to bend away from the normal. So I think we need to get something a little bit bigger than 30 degrees. Okay. And we're going to divide by the 1.00, just thinking about things to make sure that we're doing it right. Plug that into your calculator. And I believe, if I did my math right, that I got 49.5 degrees. And indeed, that is a bigger angle. So that light, if we're going to draw our picture, because it asked us to, and we like to, follow nice directions, it's going to go something like this, where this right here is whatever that was, 49.5 degrees. All right. So hopefully that helps you to kind of understand how to do these problems. You've got plenty of practice opportunities on your homework, so give those a shot. The answers to all of the questions are posted up on Canvas as well. Work together, help each other out. If you run into any major roadblocks, I will be back on Monday. Have a fantastic weekend, friends. Bye.